Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. We are doing the chapter amines, chemical properties. So let's begin with the 10th property, reaction with aryl benzene sulfonyl chloride. So benzene sulfonyl chloride, also known as Hinsberg reagent, reacts with primary and secondary amines to form sulfonamides. So this is benzene sulfonyl chloride, known as Hinsberg reagent. Primary amines will react with it to form N-alkyl benzene sulfonamide. There is a hydrogen present on the nitrogen atom, which is acidic in nature, strongly acidic, and because of the electron withdrawing sulfonyl group attached next to it. So it will dissolve in alkali to form a water-soluble salt. So on reacting primary amine with benzene sulfonyl chloride, we get N-alkyl benzene sulfonamide, which having an acidic hydrogen will dissolve in potassium hydroxide. Potassium benzene sulfonamide will be formed, which is a water-soluble salt. On acidification, it will again form alkyl benzene sulfonamide, which is insoluble. On the other hand, secondary amines react to form N-dialkyl benzene sulfonamide. H and Cl combine. HCl is given off. N-dialkyl benzene sulfonamide will be formed. It is insoluble in KOH. No acidic hydrogen over here, so it's not soluble. If we react with diethyl amine, N-diethyl benzene sulfonamide will be formed. Tertiary amines do not react with Hinsberg reagent. There will be no reaction. Next is reaction with Grignard reagent. So primary and secondary amines react with Grignard reagent to form alkanes. The alkyl group belongs to Grignard reagent. So primary amine, the H will combine with the alkyl group of the Grignard reagent to form alkane. Ethylamine will react with methyl magnesium bromide to form methane and N-ethyl magnesium bromide. Tertiary aliphatic amines do not react with the Grignard reagent because they do not have hydrogen atom attached to nitrogen atom. Reaction with carbon disulfide. It's also known as Hofmann mustard oil reaction. When primary amines react with carbon disulfide, the electrons move here and hydrogen will attach to sulfur and the remaining R and H2 carbon to form dithiophenol alkyl carbamic acid, which when heated with mercuric chloride will form alkyl isothiocyanate. It has a smell like that of mustard oil. Along with it, mercuric sulfide and HCl are formed. Because it has a smell like mustard oil, it is called Hofmann mustard oil reaction. However, aromatic amines react differently. Two molecules of aromatic amines will combine with sulfur of carbon disulfide to form H2S, and these join together to form N-diphenyl thiourea. The H2S formed reacts with KOH to form K2S, potassium sulfide and water. N-diphenyl thiourea on heating with concentrated hydrochloric acid will form phenyl isothiocyanate. Along with that, aniline hydrochloride is formed. Bond breaks from here to form C6H5 N double bond C double bond S. The H combines here to form aniline, which reacts with HCl to form aniline hydrochloride. N-diphenyl thiourea is used as an accelerator during vulcanization of rubber. Reaction with carbonyl chloride, the H of primary amine will combine with Cl of carbonyl chloride to form substituted urea. This happens on both ends along with HCl. Secondary amines will also combine to form tetraalkyl substituted urea. Aromatic amines will form alkyl isocyanate. First, acetyl aniline is formed, then N-acetyl aniline is formed, then on heating it loses HCl molecule to form phenyl isocyanate. Oxidation of amines gives different products depending upon the nature of amine and oxidizing agent. To oxidation of primary amines, primary aliphatic amines on oxidation with KMnO4 will give nitro compounds through a sequence of reactions. First, alkyl hydroxylamine is formed. Furthermore, on further oxidation, nitroso compound is formed, which on further oxidation forms nitroalkane. Primary amines in which NH2 group is attached to a tertiary carbon atom will undergo oxidation with KMnO4 to form nitro compound. Primary amine reacts with Caro's acid or H2O2 in the following way. A primary amine with primary alkyl group will form a mixture of products: hydroxamic acid, aldoxime, and N-alkyl hydroxylamine. A primary amine with secondary alkyl group will form ketoxime. A primary amine with tertiary alkyl group will form nitrosoalkane. Oxidation of secondary amines. Secondary aliphatic amines on oxidation with potassium permanganate give tetraalkyl hydrazine. Secondary amines with Caro's acid give corresponding N-hydroxyamine. Oxidation of tertiary amines. Tertiary amines are not oxidized by KMnO4 but are oxidized by Caro's acid, ozone, or hydrogen peroxide to corresponding nitrogen oxides. Amine nitrogen oxides in oxygen get attached. Oxidation of aromatic amines. Aromatic amines, because of high electron density on the benzene ring, are readily oxidized with on exposure to air or oxidizing agent, forming a complex colored product called aniline black. So aniline with acidified potassium dichromate will form an oxidized product which is colored and is called aniline black. However, controlled oxidation with acidified potassium dichromate will result in the formation of para-benzoquinone, also known as quinone. Ring substitution in aromatic amines. So aromatic amines are more reactive than benzene because of the presence of amine group on benzene ring. This amine group activates the benzene ring. The various resonating structures can clearly show that on activation the electron density increases at ortho and para positions. So first structure is benzene with 3 double bonds and lone pair of electron on nitrogen atom of amino group. The second structure will be where benzene is having double bonds on alternate position. Third structure can be constructed. These electrons move here and these here to form a double bond here with positive charge on nitrogen and a negative charge on ortho position. When these electrons move here, these move to this carbon so as to get a negative charge on para position. When these electrons move here and these to this, another negative charge on ortho position is obtained. So substitution mainly occurs at ortho or para position. Due to strong activating influence of amino group, aromatic amines will undergo electrophilic reactions readily, and so it's very difficult to stop the substitution at mono-substitution stage. It's very difficult to stop the reaction to mono-substitution state. If we want to stop it to mono-substitution stage, then we decrease the activation of the benzene ring by attaching an acetyl group to the amine group, nitrogen atom. This acetyl group is an electron withdrawing group, so it will take the lone pair of electrons of nitrogen atom towards itself, thereby decreasing the activation. So when the lone pair of electrons on nitrogen is less available, activating power of the group is decreased. This is called protection of the amine group by acetylation and can be used to control the rate of electrophilic substitution reaction. So it will prevent the formation of di and tri substituted products. Later on, we can remove the acetyl group by hydrolysis. So halogenation, when bromine water is added to aniline, 2,4,6-tribromoaniline is formed. White precipitates are formed of tribromoaniline. So this reaction is used as a test for aniline. If we want to reduce the substitution to mono substitution stage, we will decrease the activity of amine group by reacting it with acetic anhydride. Acetyl group attaches to nitrogen atom, thereby decreasing the reactivity. So when bromine is added under such conditions, bromine is attached only at ortho or para position. Later on, we can remove this acetyl group by alkaline or acid hydrolysis. Acetic COCH3 group goes away as acetic acid and ortho and para bromoanilines are formed. Nitration. Aromatic amines cannot be nitrated directly because they are readily oxidized. It is because nitric acid is a strong oxidizing agent and results in partial oxidation of the ring to form a black mass. However, under controlled condition, nitration of aniline gives unexpectedly 47% metanitroaniline. Paranitroaniline is 51% and orthonitroaniline is 2%. This is because it is strongly acidic medium. Aniline gets converted to anilinium ion. It gets protonated. This anilinium ion is deactivating and is meta-directing. So metanitroaniline is formed. To slow this process, the activity of aniline is decreased by acetylating it, and then nitration is carried out using nitric acid and concentrated sulfuric acid at 288 Kelvin. The ortho and para substituted acetyl anilines are formed. On alkaline or acidic hydrolysis, acetic acid will be given away. The COCH3 group gets removed as acetic acid and ortho and para nitroanilines are formed. Paranitroaniline is formed in major amounts. On sulfonation, on heating with sulfuric acid, aniline will give anilinium hydrogen sulfate, which on further heating at 453 to 473 Kelvin will give para-aniline sulfanilic acid. The tautomeric form of sulfanilic acid is a dipolar compound having positive and negative charges. Such kind of ions are called Zwitter ions or inner salts. Aniline does not undergo Friedel-Crafts reaction because of salt formation with aluminium chloride, the Lewis acid, which was used as a catalyst. So aniline will react with this to form aluminium chloride, where there is a positive charge on the nitrogen atom. So it acts as a strong electron withdrawing group. As a result, it reduces the electron density on the benzene ring and deactivates the ring. Coupling with diazonium salts. Aromatic amines, on reacting with the nitrous acid, form diazonium salts. When aniline is made to react with diazonium salt, benzene diazonium chloride salt under ice-cold conditions in presence of acid, the H and Cl will combine to form HCl, and these two join to form diazoaminobenzene, which gets rearranged to para-aminobenzene, which is a yellow dye. This reaction, where two molecules join together, is called coupling reaction. That's all in chemical properties of amines. Test for amines. So, solubility test. All amines are basic and hence soluble in dilute HCl. So, these amines can be regenerated from acidic medium by adding excess of alkali. Compound dissolve in HCl. They could be amines. Carbylamine reaction. Primary amines, aliphatic or aromatic amines, can be detected easily by heating the amine with chloroform and alkali. When characteristic foul smell of isocyanides is produced, this test is called carbylamine test. Human nitroso test. Secondary aliphatic or aromatic amines react with nitrous acid slowly in the cold to form yellow oily nitrosamines. These yellow oily nitrosamines give a green solution when warmed with phenol and concentrated sulfuric acid, and on dilution with water the color changes to red. It will again change to greenish blue to violet on addition of sodium hydroxide. So this test is called Lieberman's nitroso test, and it will be given by secondary amines. Dye test. On coupling with diazonium salts, aromatic amines form azo compounds in acidic medium, which are called dyes. So in this case, yellow dye is formed. Distinction between primary and secondary and tertiary amines. So we can distinguish between them. Primary amine will give carbylamine test. Bad smell of isocyanide is produced, whereas secondary and tertiary amines will not give this reaction. With nitrous acid, secondary amines will give the test. Primary amines will give nitrogen gas. Primary amines, nitrogen is given out with the formation of alcohols. Primary amine plus nitrous acid, alcohol plus nitrogen. Secondary amines, nitrosamines are formed, which give Lieberman's nitroso test. Secondary amine plus nitrous acid, nitrosamines. Lieberman's test, they will react, they will give a green solution when warmed with phenol and concentrated sulfuric acid. On dilution with water, color changes to red, and on addition of sodium hydroxide, color changes to greenish blue to violet. Tertiary amines dissolve, forming amine nitrite salts, which decompose on warming, and nitrosamine and alcohols are formed. Hinsberg test can be also used to distinguish between primary, secondary and tertiary amines. Benzenesulfonyl chloride is added and to amines and heated. The primary amines give a colored solution, which on acidification give insoluble material. Secondary amine give insoluble substance which remain unaffected by addition of acid. Tertiary amines do not react and remain insoluble in alkali and can be dissolved in acids. Azo dye test. Primary amines, aromatic primary amines can be distinguished from aliphatic amines by azo dye test. To perform this test, dissolve the primary amine in dilute HCl and cool to 273 to 278 Kelvin. Then treat this solution with ice cold solution of nitrous acid. The benzene diazonium chloride is formed. You add the resulting benzene diazonium chloride solution to cold alkaline solution of 2-naphthol. This benzene diazonium chloride will dissolve in it to give an orange-red dye of 1-phenyl-azo-2-naphthol. This is the dye test to distinguish aromatic amines from aliphatic amines. That is all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.